Good afternoon. So we're re-recording the last half of Friday's lecture because Panopto died in the middle, so I want people to have a chance at the homework guidance that was given in the lecture. So I'm going to do a quick review of Friday's lecture, starting with where things blew up. The last slide I think was in the lecture was the review of Lab 1's one syllable. So let me briefly go over that. Recall there were two versions, an iterative version, which is the one we see here, which I did describe in the first part of the lecture, so I'm not going to spend time here, but let me just quickly say there were several phases in this one syllable. First, we collected the pattern, which depended on whether it had a silent SE at the end or not. It would give me either the lowercase version of the word minus the silent S or E, or the lowercase version of the word. And then I set a counter I, which I would just advance through the word, first consuming all the consonants, including any leading Y, which is treated as a consequence, or any other consequence excluding Y, which is otherwise treated as a vowel. I would step through it and increment I. Then I would see if there was a Y at the transition after a consonant, because that counts as a vowel. And then I would exhaust all the subsequent vowels, A, E, I, O, U, but not Y, because Y following a vowel is a consonant. And then finally, I would consume any remaining consonants. And if there was nothing left, if I exhausted the entire word by the time I was done with these consumption parts, then I would be looking at a one-syllable word. And the regular expression version actually does exactly the same thing, except it's seriously shorter. You'll notice that the regular expression has the anchors starting at the start of the pattern and at the end of the pattern. So that says this regular expression needs to exhaust the entire pattern, has the optional leading Y, then followed by 0 or more consequence, which are indicated as not any of these vowels, followed by a transitional Y, optional with the question mark, followed by any number of other vowels, followed by any number of other consequence, followed by the optional S, side optional question mark, final S or E. The RE ignore case lets me handle the situation so I don't have to worry about upper and lowercase letters. And the or false ensures that this RE match, when it fails, returns none. And by having the or false, I ensure that my one syllable either returns a match object when it's successful, or it returns the Boolean false. So this is exactly the same idea. I believe I have YC and YV reversed here, but basically you get the right idea. And so this breaks down those stages and succeeds only if you exhaust the entire word given the two anchors at the beginning and the end. Okay, so that's one syllable. I then spent a little bit of time on forecast, which is really quite easy. First of all, I misspelled it. It should have been called the forecast metric without the E. Once you have a one syllable that's correct, and your code would be graded using my one syllable, so you will not be penalized for a poor one syllable. It's really very straightforward. It's just an implementation of the formula you were given. The only difficult part is the length words divided by 150, which is implicitly in the denominator here. There's the length words, there's the 150, is what normalizes this to a 150 word sample. And so that's the normalization for text length. The rest of the formula was just completely straightforward. In situations like this, it's useful to sort of ask the question, what would happen if every word were one syllable? And what would happen if no word were one syllable? And we can see here by just filling this in, if there are no one syllable words, then I'm going to have the value, this number here is going to be 0, so 0 over whatever is still 0, and I end up with a 20, which is the highest grade level. If, on the other hand, they were all one syllables, then these would all normalize to 1, and the other factors, 150 over 10, would lead me to a 5 grade level, which is the lowest grade level. So you can test this with some simple sentences that have only one syllable or no one syllable, and you can see that that's the right range. And coming up with those kinds of test cases that test the sort of extremes, the corner cases of the assignment, is a useful skill, so you should keep that in mind. Okay, the rest of the lecture I spent reviewing homework 3, and in fact I talked a little bit about the homework 3 text preparation stage. There were 3 stages in the homework, you recall. The text preparation stage followed by the vector space calculation stage, followed by the unknown identity stage. And we had covered the first two in the lecture last Wednesday, so let me briefly review the first two stages, although you can go back to last Wednesday's lecture. Essentially, all the work, or most of the work, is done by the speech initialization method, which is right here. Inside that speech init method, we have this passage which opens the file name, which containing the speech, and then creates an instance variable called text that contains all of the text in the speech with some fancy manipulation going on here. The key thing that's going on here is that I read in the speech in its entirety, and then I expand the text of that speech, which gets rid of all the apostrophes that are embedded and other apostrophe sort of possessives and contractions in the text. And it does that by using expand words. So the helper functions expand text, expand word, and flush marks do most of the work here. They are helper functions of the init method. You're asked to write these two, one of which removes the apostrophes by applying the regex that you've been given, and the other one which regularizes the text by actually applying each regular expression. Flush marks I provide to you. Flush marks basically take this regular expression, which has grouping parentheses. So any passage in the text that corresponds to either double hyphens or underscore or non-grouping paren or other paren, these are not special, these are escaped, or a comma or a colon and so on, these are all replaced with the output of the flush marks function, which was provided to you. You should study it. So the second argument of this RE sub, the first argument is a regular expression you want to replace. The second argument can either be a string to replace it with, or it can be a function that takes the group that matches this, whatever the regular expression matching is, and returns the string to replace it with. All of this is followed by a strip command, so it gets rid of any excess spaces at the ends. And that becomes the text of your speech in the speech object. We follow that with the vector spaces stage. We are going to compare speeches and unknown speeches using a cosine similarity metric on what's called the term frequency inverse document frequency measure, which is a vector. It's an n-dimensional vector shown here, W0 through Wn-1, where each weight consists of a term frequency, which is related to the number of times that term occurs in a document, and a inverse document frequency, which is the inverse, multiplicative inverse, of the number of documents that contain that term as a proportion of the size of the entire corpus, which is uppercase D. Now the 1 plus here and the log factor, all these are sort of normalizing things. The 1 plus ensures that we don't get a divide by zero error. They're just normalizing parameters. And this term frequency, inverse document frequency, is commonly used in text processing, but there are many variants of the exact formula. So this is the one that was originally proposed by Jerry Salton in the early 70s, and that's the one I've always used, and it works fine. So the way to think about this is there's a part of this, the term frequency, which is related to how many times this word appears in this document, right? Normalized by the document length, so that's why it's called a term frequency. And this part, which tells you how many documents this word appears in, divided by the number of documents in the corpus, inverse logarithm. Now, where do the words that we use here come from? In other words, these term frequency and inverse document frequency numbers all pertain to a term or a word in the document. And we have chosen to use the top K words in the corpus. So we have, for each speech, we have word frequencies by speech, but we also have the word frequency by corpus. So we're going to use the word frequency by corpus to pick the most commonly used words across all of the speeches, such that they do not appear in every document. And the reason we don't want to take words that appear in every document, like stop words, but also like words probably like America or Congress, which would appear in almost every document, is because if they appear in every document, and if you think about it, this frequency here is going to be the size of D divided by 1. This is going to be 0 or very, very close to 0. And we don't really want any of these terms to be 0 because we lose discriminatory power. So those are the parameters for devising the vector spaces. Now let's take a look at what we do with them. So let's review how we compute those vector spaces. First, once I've computed all the speech objects and all of their word frequencies, and I've updated the corpus object so it also has a word frequency that's compiled across all of the corpus, whereas the speech word frequencies are compiled within a single speech. I'm going to determine the top K words over the entire corpus, excluding any stop words, as well as words that appear in every document. Now, stop words likely appear in any document anyway, but we have a list of stop words we're going to exclude. So we're going to find the top K words, and that's going to be the terms that I use to construct my term frequency inverse document frequency vectors. So these top K words are the vector template. I'm going to store that list of words or terms in the corpus.template instance variable. I'm going to force the constituent speech objects to reconstruct their own term frequency inverse document frequency vectors based on the template that I tell them I've stored in the corpus object. Those vectors are lists of floats, which are equivalent in length to the template because there's one term frequency inverse document frequency floating point value for every word in the vector template. And then I have noticed that every template in every speech is based on the same, every vector for every speech is based on that speech's words, but on the same words in the template. So they're all comparable. And that's what's important because they have to be compared across speeches. So if I change the template, let's say I originally said I'm going to use 2,000 words in the template, and then later I said I'm going to use 300 words in the template, I have to flush all the speech vectors and reconstruct them so that they're fresh and all have the same terms, all correspond to the same terms in that template. Okay, so here's the last stage, which is probably why you've come to listen to this last part of the lecture. Assuming everything else is working, the last step is to identify an unknown speech. So let's see how that works. First of all, don't expect perfection. We don't have a lot of text for each speaker. All we have is a couple of speeches from each president. And, we don't have a very large corpus. So it's only 160 so speeches, some of which are quite short. Now, the basic idea here is that we can judge similarity between two speeches, presumably one of the known speeches, like one by Obama, and one of the unknown speeches by some unknown speaker. And I do this by computing that cosine similarity between their two term frequency inverse document frequency vectors. In fact, if I take the unknown speech, I can compute its cosine similarity to all of the known speeches. And then, whichever one of those is closest to my vector should be the most similar in terms of vocabulary and topic and so on. Let's think about it this way. Each term frequency inverse document frequency vector is like a vector in a space in some dimensionality, which is the size of the template. If I had a dimensionality of 2, then it would be like an XY floating point number pair that would point from the origin to some point in the two-dimensional Cartesian space. Cosine similarity returns a number between 1 and -1 when it's applied to two vectors. When cosine similarity is 1, the two vectors are perfectly aligned. When cosine similarity is -1, the two vectors are in inverse directions, but otherwise aligned. And anything in between represents the angle between the two vectors. So if you think of every speech as having a corresponding vector, it means that every speech has a point in that n-dimensional space that represents where that speech lays in terms of vocabulary and usage of words and so on. And we could imagine that all of Obama's speeches, say, are tightly clustered in some area of that vector space. And if I get an unknown speech that also lands in that area, it stands to reason it might have been by the same speaker. So when two vectors align, regardless of the magnitude or dimensionality, the cosine of the angle between two vectors is 1, and that holds for the Cartesian space with a dimension of 2, or our term frequency inverse document frequency with a dimension of 2,000. The vectors can still be, the cosine between the two vectors is 1. This holds true in the multidimensional space as well. I define cosine similarity between two vectors as the dot product of the two vectors divided by the cross product of those two vectors. So let's take a look at the first one. The vector dot product of two vectors of any dimension is the sum of the individual products. So this for all elements of the two vectors, v1, i and v2, I, I take each corresponding floating point number, I multiply them together, and I add that sum. So this is the pairwise product of the vectors summed together. That's the dot product. The vector cross product of those two vectors, denoted v1 cross v2, this up here is actually a times. This is a multiplication. This is the cross product, because these are regular scalar values, whereas these are vectors. So the vector 1 cross product vector 2 is the product of their magnitudes. Now think about it. In two-dimensional space, an xy vector, the length of that vector is given by x squared plus y squared square root of that quantity. So here we're going to do the same thing, where the cross product is for every dimension, 0 to n minus 1, I'm going to square that element of the vector, I'm going to add them all together, and I'm going to take their square root. I'm going to do that for both vectors, and I'm going to multiply them together, and that is the cross product of my two vectors. Now, in many real applications, what people do is they construct the term frequency inverse document frequency vectors, and they normalize those vectors to be of unit length, of length 1. Because if you do that, you can skip this division, because this product will always be 1. If the vector is of length 1, you have 1 times 1, and that just goes away. But we're not going to do that. We're actually going to compute the vector dot product, cross product every time we do cosine similarity. Okay, so that's how this works. So, like I said before, we assume the president's speeches are similar, so their word vectors all lie in sort of the same direction from the origin. Identifying an unknown speaker basically says, given the vector template, the terms I'm going to use, compute the term frequency inverse document frequency for that particular unknown speech, and then cosine similarity of that vector with each of the unknowns of the known speech vectors, define the speeches that are closest to it in the space. Now, once you do this, you could come up with a metric that says, wow, I've got the speech that's closest, the most aligned to the unknown. I'll just say that's by the same person. Or maybe I'll take a collection of 5 or 6 speeches that are nearby, and I'll do some sort of majority rule or majority vote mechanism. How you put these together is sort of up to you. What we're going to do is we're just going to, you could come up with some utility function that says, some mathematical formula based on the cosine similarities over the set to determine who the speaker is. But what we're going to do is we're just going to say, I want the top J matches, the J known speeches that are most closely aligned with the unknown speech. So I have since recomputed the answers since the Friday lecture. I have made small changes to my homework solution, and people have asked if their numbers should correspond. Much of the difference depends on how you handle the period in text. And so what I've done here is I've rerun these, and they do in fact differ a little from the numbers I showed on Friday. Your numbers should be very close. They don't have to be identical, but they should be very close. I'm using a 1,500 word vector. The unknown zero speech, which is actually by Herbert Hoover. I find that it's closest to Hoover's third speech, but also Coolidge's speeches and Harrison's speeches. The second unknown is the Gettysburg Address by Abraham Lincoln. Lincoln doesn't show up in any of these, which, as we discussed in class on Friday, the Gettysburg Address is really not like many of Abraham Lincoln's speeches. It's quite different. It's very short. It's very abstract, and it didn't really present a good match. You'll notice here the Hoover speech is a number very close enough to 1, but the best match for the Lincoln speech is really, it's not a very good match at all. The third speech, which I was corrected in class, I said it was by Richard Nixon. It's not. It's by Jerry Ford. It's when he pardons Richard Nixon. We see that came up close to Nixon and with a pretty good score, and then close to a bunch of Kennedy speeches. Now, remember, what makes these speeches close is not just the choice of words, but the topics. So if you look for who speaks about Vietnam, you're going to cluster very closely in a sort of historical part. Jerry Ford and Richard Nixon both talked about Watergate, so it's not a surprise that Nixon popped up close to this Jerry Ford speech. The third unknown speech is FDR's Day of Infamy speech. It is very close to other speeches by Franklin Roosevelt, but also by McKinley Reagan and Reagan. And finally, the Wilson speech. I don't remember which speech this was. It may be the one where he sets up the League of Nations. It's also very close to Roosevelt's speech. Your numbers here should be similar, but may not be identical. Okay, that's it. That's the super fast That's the super fast review of the Friday lecture, the second half of the Friday lecture. Post your questions to Piazza if you have stuff you want to understand better. Good luck.